in this lecture we'll answer two questions. In the first question, we find out the area of this green small circle, and in the second question, we find out the area of this quarter circle A or B using two different methods. So we start with the first question. In the drawing, we have the right line ABC. AB equals to 6 units in its length, BC equals to 8 units in its length, and the opposite AC equals to 8 units in its length. And inside this triangle, right line ABC, we have two circles. The big circle is inscribed by the right line ABC because of the fact that the big circle touches the right line ABC in 3 points, 1, 2, 3. While this green circle is not described by the right line ABC because of the fact that it touches the triangle only on 2 points. So the green circle is located inside the right line ABC and not described by the right line ABC. And our task is to find out the area of this green small circle. So first of all, we find out the radius of this big circle that is inscribed by the right line ABC. That is to say, we express the radius R of this circle in terms of A, B, and C. We express the radius R in terms of the side lengths of this right line ABC. That is to say, in terms of A, B equals to A units in its length, BC equals to B units in its length. Yeah. And again, we express the radius R of this circle that is inscribed by the right line ABC in terms of the side lengths of this right line ABC. That is to say, in terms of A, B, and C. And again, AB equals to A units in its length, BC equals to B units in its length, and AC equals to C units in its length. And the radius of this circle is defined as R. So we express the radius R in terms of A, B, and C. So first of all, we define the center of this circle. This point is point O. We define the point of tendency of tangent AB with this circle. This point is point D. Likewise, we define the point of tendency of tangent BC with this circle. This point is point E. We define the point of tendency of tangent AC with this circle. This point is point F. And again, the radius of this circle is R according to our definition. So we join points O and E together by side 9. Point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of this circle. This equals to R according to our definition. So here we can implement rule 1. The radius OE is equals to R, the radius OE is drawn to point E, that is the point of tendency of tangent BC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside, according to rule 1. Likewise, this is right angle ABC, so this angle is right angle, of course. So in the next step, we'll join points O and D together by side 9. OD is of course the radius of this circle, is equals to R. The radius OD This equals to R. The radius OD is going to point D, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is going to the point of tendency, then tangent AB will be perpendicular to the radius DO. If AB is perpendicular to DO, it means that this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside, according to the same rule, all one. So, in quadrilateral ODBE, we have 1, 2, 3 arteries. The sum of 3 arteries is 270 degrees, so 270 degrees plus the size of this fourth circle, in total must equal to 360 degrees. According to the rule, it said that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth circle must be equal to 90 degrees in its size. So inside quadrilateral ODBE, we have 4 arteries. Therefore, can we make to quadrilateral ODBE a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So rectangle ODBE, side OE must be equal to the opposite side DB. But OE is out, therefore the opposite side DB must be also equal to 1 unit in its length. Likewise, according to the same rule, in the same rectangle ODBE, side OD must be equal to the opposite side BE. But OD equals to R. OD equals to 1, therefore the opposite side BE must be also equal to 1 unit in its length. So I can find out that quadrilateral ODBE is not a rectangle, but a square. But why? Because of the fact that all of its sides are equal to each other. Each side equals to 1. So, as we know, quadrilateral ODBE is a square. What is the length of this line segment AD? From the drawing, it is very easy to see that AD in total equals to AB, that is A, minus BD, that is R. So in total, AD equals to A minus 1 unit in its length. What is the length of this AC line segment AC? From the drawing, it is very easy to see that AC in total equals to BC, that is B, minus BE, that is R. So in total, EC equals to B minus 1 unit in its length. In the next step, we will implement rule 2 in our drawing. So a piece picture on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing, we have a circle. This is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because if we focus on this common external point, point A, from this common external point A, we have two tangents to this circle, tangent AD and tangent AF. And according to rule 2, they are equal to each other. That is to say, AD equals to AF. But AD equals to A minus 1, therefore AF must be also equal to A minus 1 unit in its length. Likewise, we focus on this common external point, point C. From this common external point C, we have two tangents to this circle, tangent CE and tangent CF. And according to rule 2, they are equal to each other. That is to say, CE equals to CF. But C equals to B minus 1, and therefore CF must be also equal to B minus 1 unit in its length. AC, the opponent AC on the right side of AC equals to 3 units in its length. And it is equals to AF plus FC. So C equals to AF, AF is A minus 1, plus FC, FC is B minus 1. So then we found out that C equals to A minus R plus B minus R. So C equals to A plus B minus R is minus 2R. Here we divide this equation by 2. So we get that we relate to this equation 2R, and we subtract C simultaneously, and we get that 2R equals to A plus B minus C. So here we divide this equation by 2, and finally get that the radius R of this circle that is described by this right angle C is equal to A plus B minus C over 2. And because of the fact that the right angle ABC could be any right angle, it is a formula that is true for any circle that is described by the right angle. That is to say, the radius of a circle that is described by a right angle equals to the sum of the two perpendiculars of the right angle that blocks the circle. That is to say, it is A plus B minus the length of the hypotenuse of the right angle that blocks the circle, that is minus 3 over 2. So we use the new formula in order to find out the radius of this circle that is described by the right angle ABC. According to the new formula, the radius R of this circle that is described by the right angle ABC is equal to A plus B, that is the sum of the two perpendiculars of the right angle that blocks the circle, minus the length of the hypotenuse over 2. We define AB as A and A equals to 6. We define the perpendicular BC as B and B equals to 8 according to what is given in the question. And finally we define the hypotenuse AC as C and C equals to 10. So according to the new formula, the radius R of this circle that is described by the right angle ABC equals to A is 6 plus B is 8 minus C is 10 over 2. 6 plus 8 is 14. 14 minus 10 is 4, and 4 over 2 is 2. So in total we found out that the radius of this circle that is described by this right angle ABC is equal to 2 units in its length. We define the center of this circle, the big circle is so. We define the point of tendency of tangent AB with this circle. This point is point D, and we join points O and D together by side 9. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle, it equals to 2. So here you can implement rule 1, because we have the radius OD equals to 2, the radius OD is known to point D, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is known to the point of tendency, then tangent AB will be perpendicular to the radius DO. If AB is perpendicular to DO, it means that this angle equals to 90 degrees in its side, and this angle also equals to 90 degrees in its side according to rule 1. We define the point of tendency of tangent BC with this circle. This point is point E, and we will join points O and D together by side 9. OE is of course the radius of this circle is equals to 2. Again, according to rule 1, point is the point of density of the BC with this angle. Therefore, according to rule 1, this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside. So if you found out that in the small quadrilateral ODBE we have 1, 2, 3 right angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this small piece again, total must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this small piece again must be equal to 90 degrees inside. So inside quadrilateral DOEB we have 4 angles, and therefore can relate to quadrilateral ODBE is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the rectangle ODBE, side OE must be equal to the opposite side DB. But OE is 2, therefore the opposite side DB must be also equal to 2 units in its length. Likewise, according to the same rule, in the same rectangle ODBE, side OD must be equal to the opposite side BE. But OD is 2, therefore the opposite side BE must be also equal to 2 units in its length. So in total, we found out that quadrilateral ODBE is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Each side of this square equals to 2 units in its length. Those two circles have an external mass between them and this point. We define their touching point. This point is point L. And whenever you have an external mass between two circles, you can implement rule 10. Repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching points. In the drawing, we have those two circles that touch each other externally. This point P. The center of this circle is here at point O. The center of this circle is here at point M. The straight line that connects the centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through their touching point, that is point P. Or the straight line OM must pass through point P, that is their touching point. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. And therefore, OM total equals to OP plus PM. So we can implement rule 10 in our drawing. Likewise, in our drawing, those two circles have an external mass between them at point L. The center of this circle is at point O. We define the center of this circle, the green circle, as point K. So the center of this circle is K, and the straight line that connects the centers together is of course the straight line OK. And the straight line OK must pass through the touching point, that is point L. Okay, on the straight line OL, the straight line OK must pass for point L, that is the touching point according to rule 10. Or OKL, OLK is one straight line. So we join points O and K together by straight line, and the straight line OK must pass for point L, that is their touching point according to rule 10. It is very easy to see from the drawing that the straight line OK passes through point L, that is their touching point. And according to rule 10, OK in total equals to OL. OL is the radius of this big circle that is 2, plus LK. We define the length of LK as x. We define the radius of this green circle as x. and therefore LK is the radius of this green circle, that equals to x. So in total, we have found out that OK equals to OL, that is 2, plus LK, that is x. The radius, x is the radius of this green circle according to our definition. So OL equals to 2, LK equals to x, and therefore in total OK equals to x plus 2. So now OK equals to x plus 2 units in its length according to rule 10. In the next step, we define the point of tendency of tangent BC with this green circle. This point is point H. And we join points H and K together by side line. KH is of course the radius of this green circle, that equals to x. Again, point H is the point of tendency of tangent BC with this green circle. Therefore, according to rule 1, this angle equals to 90 degrees inside. This angle also equals to 90 degrees inside. In the next step, we define the point of tendency of tangent AC with this green circle. This point is point Y. And we join points K and Y together by side line. KY is of course the radius of this green circle, that equals to x. And according to rule 1, again, point Y is the point of tendency of tangent AC with this green circle. Therefore, according to rule 1, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size. In the next step, we will join points C and K together by side line. We define the point of tendency of tangent AC with this big circle. This point is point Z. By joining points C and K, we can do those two right triangles. This is the upper right triangle YKC, and this is the lower right triangle HKC. So in the next step, we will prove that those two right triangles can join to each other according to side rule. But before that, we'll focus on this coming standpoint, point C. From this coming standpoint, point C, we have two tangents to the green circle, tangent CY and tangent CH. And according to rule 2, they are equal to each other. That is to say, CY equals to CH. So now, we found out that CY equals to CH according to rule 2. And again, CY equals to CH according to rule 2. So in the next step, we prove that the upper right triangle YKC can go into the lower right triangle HKC according to side rule. So until now, we have to prove that the upper right triangle YKC can go to the right lower triangle KHC. So why those two right triangles can join to each other? First of all, we just now found out that cy equals to ch according to rule 2. Again, cy equals to ch according to rule 2. And again, we found out that side cy of the upper right triangle YKC is equal to side ch of the right lower triangle HKC according to rule 2. YK equals to KH. The above the area of the green circle is equals to X, and therefore they are equal to each other. So written down YK equals to KH. But again, we found out that side YK of the upper right triangle YKC is equal to side KH of the right lower triangle KHC. The above the area of the circle is equal to X, and therefore they are equal to each other. And finally, this is side KC. This is the common side that belongs to both triangles. So we can write down that KC equals to itself is the common side that belongs to both triangles. But again, KC is the common side that belongs to both triangles, so equals to itself is the common side that belongs to both triangles. So in total, we found out that all the three sides of this right upper triangle YKC are corresponding equal to all the three sides of this right lower triangle KHC. Therefore, those two right triangles can go into each other according to side rule. So now we found out that the upper right triangle YKC congruent, this is the sign of congruent, to the right lower triangle KHC according to side rule. And from the fact that those two right triangles can go into each other, we have that the following relationship exists between their angles. From the fact that those two right triangles can go into each other, we derive that those two corresponding angles must also equal to each other in their sizes. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two right triangles can go into each other, and therefore their corresponding sides, those two corresponding sides must be also equal to each other in their sizes. So if you define the size of this angle YCK as alpha, then the size of this angle, the angle KCH, must be also equal to alpha because they are equal to each other according to the rule that I mentioned. Corresponding angles and congruent triangles are equal to each other. So in total, we found out that KC is angle bisector of angle ACB. And again, KC is angle bisector of angle ACB. Why? Because of the fact that KC bisects angle ACB into two halves. Each half equals to alpha. So right now, in total, we found out that the common side KC is angle bisector. Here A B is a relation for angle bisector. So KC is angle bisector of angle ACB. Okay, again, if you found out that the common side KC is angle bisector of this angle ACB because of the fact that it bisects angle ACB into two halves, each half equals to alpha. In the next step, we join points O and Z together by side line. OZ is of course the radius of this circle is equals to 2. Point Z is the point of tendency of tangent AC with this big circle. Therefore, according to rule 1, this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size. In the next step, we will join points O and C together by straight line. So OC is the straight line according to our construction. Okay, repeat again. We join points O and C together by straight line, and therefore OC is the straight line according to our construction. In the next step, we will prove that the upper right big triangle OZC can go into this right big triangle OEC. So we have to prove that the upper right triangle OZC can go into this right lower triangle OEC. So those two right big triangles can go into each other. But before that, we will focus on this convex line point C. From this convex line point C, we have tangent CZ to the big circle. From the same convex line point C, we have also tangent CE to this big circle. And according to rule 2, they are equal to each other. That is to say, CZ equals to CE. So it is known CZ equals to CE according to rule 2. So, we just find out that side CZ of the upper right triangle OZC is equal to side CE of this right lower triangle OEC. So, it is known CZ equals to CE according to rule 2. In addition, OZ equals to OE, above the area of this big circle, that is equals to 2, and therefore they are equal to each other. OZ equals to OE, and again, side OZ of the upper right big triangle OZC is equal to side OE of the right triangle OEC. They are both the area of the circle, the big circle. This is equals to 2, and therefore they are equal to each other. And finally, OC is the common side that belongs to both triangles. Repeat again, OC is a straight line because of the fact that we join points O and C together by straight line, so OC is a straight line according to our construction. So OC equals to itself as a common side that belongs to both triangles. So until now, OC equals to itself as a common side that belongs to both triangles. So we found out that all the three sides of this upper big triangle OZC are corresponding equal to all the three sides of this right lower big triangle OEC. Therefore, those two materials can go into each other according to side rule. So until now, we found out that the upper right triangle OZC congruent, this is the sign of congruent to the right lower triangle OEC, according to side rule. And from the fact that those two right big triangles can go into each other, we will derive that their corresponding angles must be also equal to each other in the sizes. Those two corresponding angles must be also equal to each other in their sizes. according to the symbol that I've already mentioned, corresponding angles can right angles are equal to each other. Those two right angles can go into each other, so their corresponding angles must be also equal to each other in their sizes. So you define the size of it in this angle is alpha, and the size of this angle must be equal to alpha according to the rules that I mentioned. So in total we found out that OC is angle bisector of angle ACB. Again, OC is angle bisector of angle ACB because of the fact that it bisects angle ACB into two halves, each half equals to alpha. So as you know, in total we found out that OC, the common side OC, is angle bisector. Here AB is a version for angle bisector of the big angle ACB. But we only found out that KC is also angle bisector of the same angle ACB. So as you know, we only found out that KC is also the angle bisector of the same angle ACB. But we also know that the big angle ACB is only one angle bisector. Again, the big angle ACB is only one angle bisector. So as you know, the big angle ACB is only one angle bisector. So if OC is an angle bisector of angle ACB and KC is also angle bisector of the same angle ACB, it means that those 3 points O, K and C must be located on one straight line. Again, those 3 points O, K and C must be located on the same straight line. Points O, K and C must be located on the same straight line. So points O, K and C must be located on the same straight line. Here SL is the partial for straight line. And what is the straight line? The straight line is of course the angle bisector of angle ACB. And the straight line is angle bisector of angle ACB. The straight line OKC is angle bisector of angle ACB. Or in other words, we can say also that OC passes for point K. Why? Because all the 3 points are located on the same straight line, that is the angle bisector of angle ACB. So the in total we found out that OC passes for point K. What is the length of this missing line segment? Line segment EC. From the drawing, it is very easy to see that EC in total equals to BC minus BE. Again, EC in total equals to BC minus BE. So, and now, the missing line segment EC is equal to BC minus BE. So EC equals to BC, that is 8 according to what is given as the question, minus BE, that is 2 according to what we have already found out. So total EC equals to 8 minus 2 is 6. EC equals to 6 units in its length. This is 9 cent EC. This equals to 6 units in its length. In the next step, we will implement the Pythagoras theorem on this right lower triangle OEC. But again, we will implement the Pythagoras theorem on this right lower triangle OEC. Here by PT is the proportion for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, in the right triangle OEC, according to the Pythagoras theorem, OC squared, that is the square of the hypotenuse, equals to OE squared plus EC squared. So, I did now, OC squared, that is the square of the hypotenuse, equals to OE squared plus EC squared. OC is the missing side, so we leave it as it is, so it is OC squared is equal to OE squared. OE is 2, therefore OE squared is 2 squared, that is 4, plus EC squared. We just right now found out that EC equals to 6, and therefore EC squared is 6 squared, that is 36. So in total we found out that OC squared equals to 4 plus 36, that is 40. OC squared equals to 40. Here we take a root out of this equation. If I get that OC equals to the square root of 40. Here we will substitute 40 by 4 times 10. So OC equals to the square root of 4 times 10. The square root of 4 is 2, so we take 4 out of the root, so inside the root we left only with 10. Therefore in total we found out that OC equals to 2 times square root of 10 units in its length. So now the length of the hypotenuse OC of the right triangle OEC equals to 2 times square root of 10 units in its length. The next step will focus on this right triangle OEC. This right triangle OEC. This is angle alpha. This is the right angle. Therefore, this front missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this small right triangle KHC, this is angle alpha, this is the right angle, therefore this front missing angle must be equal to 90 degrees minus alpha according to the symbol that said that the sum of the angles in any triangle is equal to 180 degrees. The next step, we prove that the big right triangle OEC is similar to this small right triangle KHC according to angle similarity rule. So why those two right triangles are similar to each other? First of all, this is angle alpha. This is the common angle that belongs to both triangles. So we can write down that angle alpha equals to itself. This is the common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees also and therefore they are equal to each other. So in total, we should find out that all the angles of this big right triangle OEC are corresponding equal to all the angles of this right small triangle HKC. And therefore, those two right triangles are similar to each other according to angle similarity rule. So it is now, if we found out that the big right triangle OEC is similar, this is the sum similar to this small right triangle KHC. According to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. Repeat again. From the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side OE of the big right triangle OEC or side KH of the small right triangle KHC is equal to side OC of the big right triangle OEC or side KC of the small right triangle KHC. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between the sides. We will derive that side OE of the big right triangle OEC or side KH of the small right triangle KHC is equal to side OC of the big right triangle OEC or side HC of the small right triangle HKC. O equals to 2 or KH equals to X. And it equals to OC, we already found out that OC equals to 2 times root of 10. What is the length of KC? From the drawing it is very easy to see that KC in total equals to OC minus OK. Again, KC in total equals to OC minus OK. So it is done. We're missing 9 KC is equal to OC minus OK. So KC equals to OC minus OK. KC equals to OC. OC is 2 times root of 10. Minus OK. We found out that OK equals to X plus 2 units in itself according to rule 10. So in total we found out that the missing 97 KC is equal to 2 times root of 10 minus X plus 2. Here we'll open the brackets. Again that KC equals to 2 times root of 10. After we open the brackets, here we have minus X minus 2. So in total we found out that the missing 97 KC equals to 2 times root of 10 minus X minus 2. So that is now. This is the missing 97 KC that equals to 2 times root of 10 minus X minus 2. So we should find out that KC here in this equation equals to 2 times square root of 10 minus x minus 2. So today we should find out that 2 over x equals to 2 times square root of 10 over 2 times square root of 10 minus x minus 2. Here we have 2 on both sides of this equation, so 2 will get cancelled. So after we cancel 2, we cross multiply this equation, and we get that after we cross multiply this equation, this side of the equation we have 2 times square root of 10 minus x minus 2 equals to x times square root of 10. But again, after we cross multiply this equation, it goes on from down that 2 times square root of 10 minus x minus 2 equals to x times square root of 10. Here we will add we will add x to this equation, and get that in this side of the equation we left only with 2 times square root of 10 minus 2. So after we did x to this equation, and on the other side of the equation we have x times square root of 10 plus x. We added x to this equation. So in the next step, we will take 2 as a common factor out of those two expressions. So inside the brackets we left only the square root of 10 minus 1, and is equals to x times square root of 10 plus x. So here we take x as a common factor from those two expressions. So inside the brackets we left with square root of 10 plus 1. So total we found out that 2 times square root of 10 minus 1 equals to x times square root of 10 plus 1. Here we will divide this equation by square root of 10 minus 1. We will divide this equation by square root of 10 plus 1. And we get that x equals to 2 times square root of 10 minus 1 over square root of 10 plus 1. And again, in total, we found out that x equals to 2 times square root of 10 minus 1 over square root of 10 plus 1. So it is down here. Found out that actually that x equals to 2 times square root of 10 minus 1 over square root of 10 plus 1. X is the radius of this green circle, that is the radius that we are looking for in this question. After we find out the value of x, just have to square it and multiply it by pi, and this will be the area of this green circle. Repeat again, the area of this green circle is equal to pi x squared. So we just have to find out x, and we immediately find out also the area of this green circle. So then we found out that x equals to 2 times square root of 10 minus 1 over square root of 10 plus 1. So here we will multiply both the numerator and the denominator of this expression by square root of 10 minus 1. So x equals to 2 times square root of 10 minus 1. So we multiply the numerator by square root of 10 minus 1 over, we have here square root of 10 plus 1, so I copy this expression here. And we have to multiply also the denominator by square root of 10 minus 1. So in total we found out that x, this is the radius of the green circle, is equal to 2 times square root of 10 minus 1 times square root of 10 minus 1 equals to square root of 10 minus 1 squared. Here we have square root of 10 plus 1 times square root of 10 minus 1. We will use the following algebraic identity to find out the value of this expression. The algebraic identity says that a plus b times a minus b equals to a square minus b square. So according to this algebraic identity, if you just substitute a by square root of 10 and b by 1, we get that square root of 10 plus 1 times square root of 10 minus 1 equals to a square minus b square. So this is to say this equals to square root of 10 squared, that is 10, over minus square root of b square. So it is minus square root of 1 squared, that is 1. So in total, in the denominator we have 10 minus 1, that is 9. In total, this expression, square root of 10 plus 1 times square root of 10 minus 1, according to this algebraic identity, equals to 10 minus 1, that is 9. So we found out in total that x equals to 2 times square root of 10 minus 1 square over 10 minus 1, that is 9. So x in total equals to 2. We open the brackets of this expression, square root of 10 minus 1 square equals to the square root of 10 square, that is 10, plus 1 square, that is 1, minus 2 times square root of 10 times 1. Divided by 10 minus 1 is 9. So in total, we found out that the radius x of the green circle, the green small circle, equals to 2 9ths. Inside the brackets we have 10 plus 1 is 11, minus 2 times square root of 10. But again, in total, if you found out that x, that is the radius of the small green circle, equals to 2 9ths times 11 minus 2 times square root of 10 units in its length. Our task is to find out the area of this green circle. So the area of any circle equals to pi times the radius of the circle squared. But again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of this green circle must be equal to pi times the radius of this green circle squared. The radius is x, therefore it is pi x squared. So in total, we found out that the area of the green small circle equals to pi x squared. So it is pi times x squared. X is 2 9ths times 11 minus 2 times square root of 10, and we have to square x, so it is all squared. So in total, the area of the green small circle equals to pi. We have square on both expressions, so first of all, we square 2 9ths. 2 9ths squared is 2 squared, that is 4, over 9 squared, that is 81. We have also to square the other expression, that is to say, it is 11 minus 2 times square root of 10 squared. So in total, we found out that the area of the green small circle equals to 4 pi 4 pi over 81. We have here 11 minus 2 times square root of 10 squared. This actually equals to 11 squared, that is 121, plus 2 times square root of 10 squared, that is actually 2 squared, that is 4, times square root of 10 squared, that is 10, and 4 times 10 is 40. Minus 2 times 11 is minus 22. Minus 22 times 2 is minus 44. So in total, this minus 44 times square root of 10 units is so in total, we found out that the area of the green small circle is equal to 4 pi over 81. Inside the brackets we have 121 plus 40, this is 161, minus 2 times minus 44. This is this digit is 4, so it is minus 44 times square root of 10. And again, in total, we should find out that the area of the green circle, that is the area that we're looking for in this question, is equal to 4 pi over 81 times 161 minus 44 times square root of 10 units is actually the value of this expression in total is equal to 274.7 square root in size. And that is the answer to the first question. Okay, again, if we found out in total that the area of this green circle, green small circle, equals to 274.7 square root in size. So we finish with the first question. In the next step, I will present you the second question, and we will solve the second question by using two different methods. In the second question, our task is to find out the area of this quarter circle A or B. And again, our task is to find out the area of this quarter circle A or B. So in the drawing, we have quarter circle A or B. This is a right angle, this is angle PQB, this is also a right angle. In addition, we know that QB equals to 1 unit in itself, and also PQ equals to OQ. Again, our task is to find out the area of this quarter circle A or B. So, first of all, we define the radius of this quarter circle as x. AO equals to OB, the above the radius of the circle, this equals to x. So AO equals to x according to our definition. OB also equals to x, it is the radius of this quarter circle. But it is given as a question that OQ equals to PQ. What is the left of OQ? OQ equals to OB, that is x, minus QB, that is 1. So in total, OQ equals to x minus 1. But OQ equals to PQ according to what is given as a question. And OQ equals to x minus 1, therefore PQ must also equal to x minus 1 in its length. In the next step, we will complete this quarter circle to a circle. So completed the quarter circle to a circle. Then we'll extend the radius of B by sideline until it touches the circle. And we find the touching point of the extended radius OB with this circle. This point is point N. ON is the radius of this circle. Is equals to X. Likewise, we'll extend last side PQ by sideline until it touches the circle. And we'll define the touching point of the extended last side PQ with this circle. This point is point M. Actually, we have here PQ and QM. The upper semicircle is symmetric to the lower semicircle. If we divide the circle into two parts, we get that the upper semicircle is symmetric to the lower semicircle. And the axis of symmetry between the upper semicircle and the lower semicircle is NB. Again, NB is the axis of symmetry on the upper semicircle with the lower semicircle. So, if we flip this semicircle towards us, then point P will merge with point M because of the fact that QM is the mirror image of QP. Again, because of the fact that QM is the mirror image of PQ, if we flip this semicircle towards us, point P will merge with point M, and therefore QP equals to QM. But QP is x minus 1, therefore QM must be also equal to x minus 1 unit in its length. Like when you look in the mirror, you see yourself exactly as the same size of as you are in reality, but in the opposite direction. QM is the mirror image of PQ, therefore QM must be equal to PQ in its length. PQ is x minus 1, therefore QM must be also equal to x minus 1 in its length. So in the next step, we will implement all 65 in our drawing. So I paint quickly on all 65. All 65 is true in any circle. So in any circle, if chord AB intersects with chord CD at point O, then the following equation is to AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. And again, in the moment we have a circle, this is chord AB that intersects with chord CD at point O. So whenever you have two chords that intersect with each other, the following equation is to AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement all 65 in our drawing. One put in our drawing. This is chord NB that intersects with chord PM at point Q. Again, chord NB intersects with chord PM at point Q. So all the requirements of all 65 are satisfied, and therefore we can implement here all 65. So until now, we shall find out that in our original drawing, we have chord NB intersects with chord PM at point Q. the intersection point of chord NB with chord PM occurs at point Q. Again. Now we're gonna go in. Chord NB intersects with chord PM at point Q. Therefore, according to Rule 65, the following equation is true. NQ times QB equals to PQ times QM. Again, NQ times QB equals to PQ times QM. So, write it down. NQ times QB equals to PQ times QM. So, according to Rule 65, in our original domain, the following equation is true. NQ times QB equals to PQ times QM. This equation is the implementation of Rule 65 in our domain. NQ equals to NO, that is X, plus OQ, that is X minus 1. So in total, NQ equals to 2X minus 1 times QB. QB is 1. And this equals to PQ. PQ is X minus 1 times QM. QM is also X minus 1. In total, if you found out that 2X minus 1 times 1 equals to X minus 1 times X minus 1. So it is 2X minus 1 equals to X minus 1 square. 2X minus 1 equals to X minus 1 square. We'll open the brackets of this expression and we get that X minus 1 square equals to X squared plus 1 squared, that is 1, minus 2 times X times 1, that is minus 2X. Here we'll subtract 2X from this equation and we get that minus 1 equals to X1 plus 1, minus 2X is minus 4X. Here we'll add 1 to this equation. So in this side of the equation we left in nothing, that is to say 0. When on the other side of the equation, we have X squared. 1 plus 1 is 2, minus 4X. So in total, if you found out that X squared minus 4X plus 2 equals to 0. This is a quadratic equation, and the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus root of b squared minus 4 times a times c over 2a. Now a specific quadratic equation, that is to say x squared minus 4x plus 2 equals to 0. The variable that we're looking for is x, and x is the radius of this quarter second. So you know, x is the radius of the quarter second. Another specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to minus 4, and finally the coefficient c equals to 2. We have all the data that is needed in order to find out the value of x, that is the radius of the quarter circle. You just have to put this data inside this general formula for x, and this way we find out the value of x, because x might have two solutions. We'll do it now and we get that x equals to minus b. b is minus 4, therefore minus b is minus 4, that is plus 4, plus minus square root of b squared. b is minus 4, therefore b squared is minus 4 squared, that is 16, minus 4 times a. a is 1, so minus 4 times 1 is minus 4, times c. c is 2, so minus 4 times 2 is minus 8. So minus 4 times a, c is minus 8. Divided by 2a. a is 1, so 2a is 2 times 1, that is 2. So in total we found out that x, that is the radius of the quarter circle, equals to 4 plus minus. Inside the root we have 16 minus 8 is 8 over 2. So x equals to 4 plus minus. We substitute 8 by 4 times 2. Over 2. X equals to 4 plus minus. The square root of 4 is 2. So inside the root we left only with 2. So in total we found out that x equals to 4 over 2 is 2, plus minus. We have 2 in the denominator, the denominators to get cancelled, and we left only with square root of 2. So in total we found out that x equals to 2 plus minus square root of 2. X, that is the radius of the quarter circle, equals to either 2 plus square root of 2 units in terms, or the other solution is that x equals to 2 minus square root of 2 units in terms. So if you know, x have two solutions. X equals to 2 plus minus square root of 2. So the first solution for x is that x is equals to 2 minus square root of 2. 2 minus square root of 2 is 0.59. So according to the first solution, for x, that is the radius of the quarter circle, equals to 0.59 units in its length. We already found out that OQ equals to x minus 1. Now that OQ equals to x minus 1 units in its length. So OQ is a length, and as a length it must be a positive number. OQ equals to x minus 1, so it means that x minus 1 must be a positive number. What is a positive number? A positive number is a number that is greater than 0. So OQ must be greater than 0. OQ is x minus 1, so x minus 1 must be greater than 0. This is a positive number. Here we add 1 to this inequality, and we get that x must be greater than 1. X must be greater than 1, but according to the first solution, for x equals to 0.59, that is definitely less than 1. X must be greater than 1, so this solution is the correct solution. So we cancel the solution for x, and we'll take into account only the second solution for x. The second solution for x is as follows. X equals to 2 plus square root of 2. It means again, the radius x of the quarter circle equals to 2 plus square root of 2 units in itself according to the second solution for x. Then again, our task is to find out the area of this quarter circle A or B. So what is the area of quarter circle A or B? The area of the quarter circle A or B equals to the area of the circle that is pi x squared over 4. Then again, the area of quarter circle A or B must be equal to pi x squared over 4. Because x is the radius of the quarter circle. So it is pi over 4 times x squared. X is 2 plus square root of 2. Therefore, x squared must be equal to 2 plus square root of 2 squared. So in total, we found out that the area of this quarter circle A or B equals to pi over 4 times 2 plus square root of 2 squared. Square it in its size. Actually, the value of this expression is 9.155 square root in its size. So in total, we found out that the area that we are looking for in this question, that is the area of this quarter circle A or B, is equal to 9.155 square root in its size. So we finished with the first method. In the next step, I'll present to you how to find out the area of this quarter circle A or B according to the second method. In the second method, we define the radius of this quarter circle as x, so AO equals to OB equals to x, they are both the radius of the quarter circle. QO, in the first method we only found out that QO equals to OB minus QB. OB is x, QB is 1, so in total OQ equals to x minus 1 unit in its length. But OQ equals to PQ according to what is given in this equation, and OQ is x minus 1, therefore PQ must be also equal to x minus 1 units in its length. OB is the radius of this quarter circle, therefore it is definitely a straight line. So if you focus on the upper side of this straight line, OB at point Q, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the areas on one side of the straight line is equal to 180 degrees. So which angles we have the upper side of the straight line OB at point Q, we have this angle that is right angle plus this missing angle, total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we will join points O and P together by straight line. By joining points O and P, we can get the right green triangle OPQ. Point O is the center of the quarter circle, point P is the point of the quarter circle itself, therefore OP is the radius of the quarter circle, that equals to x according to our definition. In the next step, we will implement the Pythagoras theorem on this green right triangle OPQ. But again, we will implement the Pythagoras theorem on this green right triangle OPQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. Repeat again. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. So OP is the hypotenuse in the right angle PQ. Here by PT is the expression for Pythagoras theorem. The OP is the hypotenuse, so OP square, according to the Pythagoras theorem, OP square, that is the square of the hypotenuse, equals to PQ square plus OQ square. This again, according to the Pythagoras theorem, this green right triangle PQ, OP square, that is the square of the hypotenuse, equals to PQ square plus OQ square. OP is x, therefore OP square is x square, and it equals to QP square. QP is x minus 1, therefore QP square is x minus 1 square, plus OQ square. OQ is also x minus 1, therefore OQ square is x minus 1 square. So in total, we should find out that x squared equals to x minus 1 square plus x minus 1 square. That is to say, x squared equals to 2 times x minus 1 square. Okay, so here we have x squared equals to 2 times. Here we'll open the brackets of this expression x minus 1 square. X minus 1 square equals to x squared plus 1 squared, that is 1, minus 2 times x times 1, that is minus 2x. So in total we should find out that x squared equals to 2 times x squared plus 1 minus 2x. So x squared equals to, we'll open the brackets here, it is 2 times x squared. 2 times 1 is 2. 2 times 1 is 2x, is minus 4x. So in total, if you want to know that x squared equals to 2x squared plus 2 minus 4x. Here we subtract x squared from this equation. So in this side of the equation we left with nothing, this is to say 0. While on the other side of the equation, 2x squared minus x squared is x squared minus 4x plus 2 equals to 0. But again, in total, we should find out that x squared minus 4x plus 2 equals to 0. This is exactly the same quadratic equation that we had in the first method. So in the first method, we found out that the solution of this quadratic equation is that x equals to 2 plus square root of 2 is inside. And therefore, the area of the quarter circle, AOB, equals to pi x squared over 4. Pi x squared over 4. So it is pi over 4 times x squared. X is 2 plus square root of 2, therefore x squared is 2 plus square root of 2 squared. So in total, the area of quarter circle AOB equals to pi over 4 times 2 plus square root of 2 squared. The value of this expression is actually 9.155 square root in size. So here, in both methods, we found out that the area of this quarter circle AOB is equal to 9.155 square root in size. So we finish with the second method, the second question. So in the next step, outside the lecture, we start with the repetition of the first question, and then we repeat on the solution of this second question on both methods. The first question of our test is to find out the area of this small circle. So in the drawing, we have the right angle ABC. AB equals to 6, BC equals to 8, the opposite AC equals to 10. Inside this right angle ABC, we have those two circles that touch each other somewhere at this point. The big circle touches the triangle 3 points, 1, 2, 3, 1, 2, 3, and therefore it is inscribed by the right angle ABC. While the second small circle touches the triangle only 2 points, therefore it is not inscribed by triangle ABC, but it is located inside triangle ABC. So, and again our test is to find out the area of this small circle. So, in the first step, we developed a formula for a radius of any circle that is inscribed by a right angle. This is the right angle ABC that could be any triangle. Inside this right angle ABC, we have this circle that is described by the right angle ABC. The radius of this circle is R, and our test is to find out, to express the radius R in terms of the side lengths of this triangle ABC. AB equals to A units in itself, BC equals to B units in itself, the opposite AC equals to C units in itself. Again, our test is to express the radius R of this circle that is described by the right angle ABC in terms of A, B, and C. So in order to find out to express the radius R in terms of A, B, and C, we just have to implement rule 1 and 2 on this drawing. Again, this is triangle ABC that could be any triangle. Therefore, the new formula that we find out is be true for any right triangle that is described as any circle that is described by a right triangle, or any right triangle that blocks a circle. Therefore, we can use the new formula in order to find out the radius of this big circle that is described by triangle ABC. So, actually, this is triangle ABC, the right triangle ABC that could be any right triangle. Inside this right triangle ABC, we have this circle that is described by the right triangle ABC. The radius of this circle is R, and our text is to express the radius R of this circle in terms of A, B, and C. Okay, again, in triangle ABC, side AB equals to A units in itself, side BC equals to B units in itself, and the opposite AC equals to C units in itself. So first of all, we implemented rule 1 in our drawing. Define the center of this circle as O. We define the point of tendency of tangent AB with this circle, this point is point D. We define the point of tendency of tangent BC with this circle, this point is point E. And finally, we define the point of tendency of tangent AC with this circle, this point is point F. We join points O and D together by straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of the circle, is equals to R. The radius of D is equals to R, the radius of D is drawn to point D, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius DO. If AB is perpendicular to DO, then this angle corresponds to and this angle corresponds to according to rule 1. Likewise, we join points O and D together by straight line. Point E is the point of tendency of tangent BC with this circle. So OE is the radius of the circle that is equals to R. Again, OE is the radius of the circle that is equals to R. And according to rule 1, those circles are both right angles. So in quadrilateral ODBE, we have 1, 2, 3 right angles. Therefore, this fourth circle is equal to 90 degrees inside, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral ODBE, we have 4 angles, and therefore we can add to quadrilateral ODBE is a rectangle. But we also know that the opposite sides of the rectangle are equal to each other. So in rectangle ODBE, side OD must be equal to the opposite side BE. But OD is out, therefore the opposite side BE must be also equal to R units in itself. And likewise, according to the same rule, in the same rectangle ODBE, the opposite sides are equal to each other. So OE equals to OB. OE is out, therefore OB must be also equal to R in itself. So in total, if you found out that quadrilateral ODBE is not rectangle, is not rectangle but a square, right, because of the fact that all three sides are equal to each other. Each side equals to R. What is the length of line 17C? EC equals to BC, that is B, minus BE, that is R. So in total, EC equals to B minus R in itself. Likewise, what is the length of line 7 AD? AD equals to AB, that is A, minus BD, that is R. So in total, AD equals to A minus R in itself. The next step, we focus on this common sum point A. From this common sum point A, we have two tangents to this circle, tangent AD and tangent AF. And the only two they are equal to each other. They are equal to each other. That is to say, AD equals to AF. But AD is A minus R, therefore AF must be also equal to A minus R. It's in itself, we only two. Likewise, we focus on this common sum point C. From this common sum point C, we have two tangents to this circle, tangent CE and tangent CF. And if only two they are equal to each other, that is to say CE equals to CF. But CE equals to B minus R, therefore CF must be also equal to B minus R in itself. So in total, the hypotenuse AC equals to C according to our definition. And it is equals to AF plus FC. So C equals to AF plus FC. C equals to AF, that is A minus R, minus FC, that is B minus R. So to that, we should find out that C equals to A minus R plus B minus R. That is to say, C equals to A plus B minus R is minus 2R. Here we added 2R to this equation and subtract C simultaneously. We find out that 2R equals to A plus B minus C. Here we divided this equation by 2 and find out that the radius R of this circle that is described by right angle BC equals to A plus B minus C over 2. Because of the fact that the right angle BC could be an triangle, a new formula that is good for any right angle that blocks a circle. So the radius R of this circle that is described by right angle BC equals to the sum of its two perpendiculars, that is to say A plus B, minus the length of the hypotenuse, that is C over 2. So we can actually implement the new formula in our right angle BC in order to find out the radius of this big circle. So according to the new formula, the radius R of this circle equals to A plus B minus C over 2. The radius R equals to A plus B minus C over 2. We define AB as A and A equals to 6. We define BC as B and B equals to 8. We define AC as C, and C equals to 10. And again, the radius R of this circle equals to A plus B minus C over 2. So the radius R equals to A is 6, plus B is 8, minus C is 10 over 2. So R equals to 6 plus 8 is 14, 14 minus 10 is 4, and 4 over 2 is 2. So in total, we know that the radius R of this big circle that is described by this right angle BC is equals to 2 units in its length. In the next step, we define the point of tendency of tangent AB with this circle. This point is point D. Likewise, we define the point of tendency of tangent BC with this circle. This point is point E. We define the point of tendency of tangent AC with this circle. This point is point Z. We define the point of tendency of tangent AC with this small circle. This point is point Y. So here we define the center of this circle. This point is point O. And we join points on the other side line. Point O is the center of the big circle, point D is the point of the circle itself, therefore D is the radius of this circle. This is equals to 2. So equals to 2. This big circle. Here we can implement all 1. The radius OD is equals to 2. The radius OD is 1 to point D, that is the point of tendency of tangent AB with this circle. Whenever you have radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius DO. If AB is perpendicular to DO, it means that this circle must be 90 degrees, and this circle must be 90 degrees according to rule 1. Likewise, we join points O and D together with side line. Point E is the point of tendency of tangent BC with this big circle. So OE is the radius of this circle, this is equals to 2. According to rule 1, those figures are both right degrees. So in quadrilateral ODBE, we have 1, 2, 3 layers, and therefore this fourth missing layer must be equal to 90 degrees in size. According to all the third and sum of layers in the quadrangle is equal to 360 degrees. And therefore this fourth missing layer must be equal to 90 degrees in size. So in quadrangle ODBE we have 4 layers, and therefore we can go to quadrangle ODBE is rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ODBE, side OD must be equal to the opposite side BE, but OD is 2, therefore the opposite side BE must be also equal to 2 units in itself. Likewise, according to the symbol, in the same rectangle ODBE, side OE must be equal to the opposite side DB, but OE is 2, therefore the opposite side DB must be also equal to 2 units in itself. So in total, we found out that quadrangle ODBE is not a rectangle but a sphere, because of the fact that all of its sides are equal to each other, each side equals to 2. We have an example between those two circles at point L. Therefore, we can implement rule 10. Implementing rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the circles together passes through their touching points. In the drawing, we have those two circles that touch each other externally at this point, point P. The center of this circle is 0.0. The center of this circle is 0.10. The straight line that connects the circles together is of course the straight line OM. And this straight line OM, according to this rule 10, must pass for their touching point at this point P. Again, the straight line OM must pass for point P, that is their touching point. OPM is one straight line. Again, OPM is one straight line. If OPM is one straight line, it means that OM equals to OP plus PM. So we can implement rule 10 in our drawing. In our drawing, those two circles and externals between them at point A. The center of this circle is here at point O. The center of this circle is here at point K. The straight line that connects the circles just together is of course the straight line OK. The straight line OK must pass for point A, that is the touching point according to rule 10. Again, the straight line OK must pass for the touching point, that is point L. OLK is one straight line. Again, according to rule 10, OLK is one straight line. OL is the radius of this big circle, that is 2. LK is the radius of this green circle, that is x according to our definition. So in total, OK equals to OL plus LK according to rule 10. Therefore, in total, OK equals to OL, that is 2, plus LK, that is x. In total, OK equals to x plus 2 units in its length. In the next step, so point K is the center of the green circle. So we join points K and H together by straight line. Point S is the point of tendency BC with this small circle. Therefore, according to, again, KH is the radius of this circle, that is x. According to rule 1, those two angles are both right angles. Likewise, we join points Y and K together by straight line. YK is the radius of this circle, that is equals to x. Those two angles are both right angles according to rule 1. The next step we join, we focus on this common sum point C. For this common sum point C, we have two tangents to this small circle, tangent CY and tangent CH. According to rule 2, they are equal to each other. That is to say, CY equals to CH. Okay, CY equals to CH. So in the next step, we join points C and K together by straight line. In this way, by joining points C and K, we get those two right angles, the upper right angle YKC and the lower right angle KHC. So in the next step, we proved that those two right angles can go into each other according to side rule. Why those two right angles can go into each other? First of all, we just right now found out that CY equals to CH. In addition, those two line segments are both the radius of the circle, that is equals to x, and therefore they are equal to each other. And finally, CK is the common side that belongs to both triangles, so we can write down that CK equals to itself is the common side that belongs to both triangles. In total, we found out that all the three sides of this upper right triangle YKC are equal to all the three sides of this lower right triangle KHC. Therefore, those two right triangles can go into each other according to side rule. And again, in total, we found out that the upper right triangle YKC can went, this is the side can went to the right lower triangle KHC according to side rule. And from the fact that those two right triangles can go to each other, we will derive that their corresponding angles are equal to each other and their sizes. Those two corresponding angles must be equal to each other and their sizes. Their sizes according to the rule that says that corresponding angles and congruent angles are equal to each other. Those two angles congruent to each other, those two corresponding angles must be also equal to each other and their sizes. So if we find the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. And therefore, KC is the angle bisector of angle ACK. Again, KC is the angle bisector of angle ACK. Why? Because of the fact that KC bisects angle ACB into two halves, each half equals to alpha. Again, in total, if you found out that KC is the angle bisector, AB is the ratio of angle bisector of angle ACB. In the next step, we prove that those two right big triangles can go into each other according to side rule. Actually, before that, we join points C and O together with side line. So CO is the side line according to our construction. So in the next step, we prove that those two right big triangles can go into each other according to side rule. We only join points O and Z together with side line, and those two angles are both right angles, and OZ is the radius of the circle that is 2, and OE is also the radius of the big circle that is 2, and those two angles are both right angles. So we prove that those two right big triangles can go into each other according to side rule. If we focus on this common example point C, for this common example point C, we have two tangents to the big circle, tangent CZ and tangent CE, and according to rule 2, they are equal to each other. That is to say, CZ equals to CE. Okay. So, first of all, CZ equals to CE. In addition, we know that according to rule 2, ZO equals to OE. They are both the area of the big circle, equals to 2, and therefore they are equal to each other. And finally, OC is the common side that belongs to both triangles, so we can find out that OC equals to itself is the common side that belongs to both triangles. In total, we found out that all the three sides of this right triangle OZC correspond equal to all the three sides of this right triangle OEC, and therefore those two right triangles can go to each other according to side rule. But again, in total, we found out that the upper right triangle OZC congruent, this is the sign of congruent to the right lower triangle OEC according to side rule. And from the fact that those two right big triangles can go to each other, we will derive that the corresponding angles are equal to each other and their sizes. Those are the two corresponding angles of those two right triangles that can go to each other, and therefore must be equal to each other in their sizes according to the sum rule that I already mentioned. Corresponding angles and congruent triangles are equal to each other. Those two right triangles can go to each other, and their corresponding angles must be equal to each other in their sizes. Those are the two corresponding angles that must be also equal to each other in their sizes. So if you find the size of this angle as alpha, then the size of this angle must be also equal to alpha according to the rule that I mentioned. So in total, we found out that OC is also the angle bisector of angle ACB. Again, OC is the angle bisector of angle ACB. Why? Because of the fact that OC bisects angle ACB into two halves, each half equals to alpha. So we have found out that OC is the angle bisector of angle ACB. But we only found out that KC is also angle bisector of angle ACB. So OC and KC are both the angle bisector of angle ACB. But we know that angle ACB is only one angle bisector. Angle ACB is only one angle bisector. The big angle ACB is only one angle bisector. So if OC and KC are both angle bisector of angle ACB, it means that points O, K, and C must be located on one side line. Points O, K, and C must be located on one side line. And what is the side line? The side line is of course the angle bisector of angle ACB. Why? Because of the fact that angle ACB is only one angle bisector. So O, K, and C are located on one side line, and the side line is the angle bisector of angle ACB. And therefore, OC passes for point K. OC passes for point K because OK are located on the same side line. So OC passes for point K. so EC equals to BC, that is 8, minus BE, that is 2. So total is equals to 8 minus 2, that is 6. And again, last side is equals to BC minus BE. BC is 8, BE is 2, so in total is equals to 8 minus 2, that is 6. Is equals to 6 units in itself. The next step, we present the Pythagoras theorem on this right lower B triangle OEC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the scores of the perpendicular. So in this right triangle OEC, OC squared, that is the square of the hypotenuse, equals to OE squared plus EC squared. But again, the right lower triangle OEC, according to the Pythagoras theorem, OC squared, that is the square of the hypotenuse, equals to OE squared plus EC squared. OC is the missing side, so we leave it as it is. And this equals to OE squared. OE is 2, therefore OE squared is 2 squared, that is 4. Plus EC squared. EC is 6, therefore EC squared is 6 squared, that is 36. So in total, we found out that OC squared equals to 4 plus 36, that is 40. OC squared equals to 40. We took out of this equation. We found out that OC equals to the square root of 40. We substituted 40 by 4 times 10. Then we took 4 out of the root. The square root of 4 is of course 2. So inside the root we have to leave 10. So in total, if you found out the hypotenuse OC equals to 2 times square root of 10 units in itself. Until the end, this is the hypotenuse OC of the right triangle OEC. This equals to 2 times square root of 10 units in itself. OC equals to 2 times square root of 10 units in itself. The next step we focus on the right big triangle OEC. This angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees, it is the sum of the angles in any triangle. Likewise, in the small right triangle KHC, this is angle alpha, this is a right angle, therefore this first missing angle must be equal to 90 degrees minus alpha. According to the sum of the set, that the sum of the angles in any triangle is equal to 180 degrees. The next step we prove that the right triangle OEC is similar to the small right triangle KHC according to angle similar to 1. So why those two right triangles are similar to each other? First of all, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself, it's a common angle that belongs to both triangles. Likewise, those two angles are both right angles and therefore they are equal to each other. We find those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So in total, we found out that all the figures of this right big triangle OEC correspond equal to all the figures of this small right triangle KHC. Again, all the figures of this right triangle OEC correspond equal to all the figures of this small right triangle KHC. Therefore, those two right triangles are similar to each other according to angle similar to 1. And again, total, if you found out that the big triangle OEC is similar, this is the sign of similar to the small right triangle KHC according to angle similar to 1. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side OE of the big right triangle OEC over side K8 of the small right triangle KHC is equals to OC of the big right triangle OEC over side KC of the small right triangle KHC. Because again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side OE of the big triangle OEC over side K8 of the small triangle KC equals to side OC of the big triangle OEC over side AC of the small triangle AC. What is the length of KC? KC equals to OC minus OK. But again, KC equals to OC minus OK. KC equals to OC minus OK. KC equals to OC. OC equals to 2 times square root of 10 minus OK. OK equals to x plus 2. So if you found out that KC equals to OC 2 times square root of 10, or OK, x plus 2. So total KC equals to 2 minus x plus 2. We open the brackets here. In total, actually found out that KC equals to 2. After we open the brackets, we have here minus x minus 2. So in total, KC equals to 2 times square root of 10 minus x minus 2. So, found out that because of the fact that those two right angles are similar to each other, the following relationship exists between their sides. OE over KH equals to OC over HC. OE is 2, KH is x, OC is 10 times square root of 10, and KC is 2 times square root of 10 minus x minus 2. So if you found out that 2 over x equals to 2 times square root of 10 over 2 times square root of 10 minus x minus 2. We have 2 on both sides of this equation, so 2 gets cancelled. After we cancel 2, we of course multiply this equation, and we found out that after we multiply this equation, we found out that 2 times square root of 10 minus x minus 2 equals to x times square root of 10. Here we added x to this equation, and we found out that in this side of the equation we left only with 2 times square root of 10 minus 2, and on the other side of the equation we have x times square root of 10 plus x. Here we took 2 out of this as a common factor from those two expressions, so inside the brackets we left with square root of 10 minus 1. Here we took x as a common factor from those two expressions. We took out x as a common factor from those two expressions, so inside the brackets we left with square root of 10 minus 1. Here we divided this equation by square root of 10 plus 1, and we found out that x equals to 2 times square root of 10 minus 1 over square root of 10 plus 1. And again, so now if you found out that x equals to 2 times square root of 10 minus 1 over square root of 10 plus 1. Here we multiplied both the numerator and the denominator of this expression by square root of 10 minus 1. Yeah, multiply the numerator by square root of 10 minus 1 and the denominator by square root of 10 minus 1. This, of course, is allowable to multiply anything by 1. Okay, so now if you found out that x equals to 2 times square root of 10 minus 1 times square root of 10 minus 1 over square root of 10 plus 1 over square root times square root of 10 minus 1. So here we have 2 times square root of 10 minus 1 times square root of 10 minus 1 square root of 10 minus 1 squared, and then the denominator will square root of 10 plus 1 times square root of 10 minus 1. According to this algebraic identity, a plus b times a minus b equals to a squared minus b squared. So if we choose a as square root of 10 and b as 1, then according to this algebraic identity, this expression equals to the square root of 10 squared, that is 10, minus 1 squared, that is 1. So we should know that this expression equals to 10 minus 1, that is 9. This expression equals to 2 times square root of 1 squared. So in total we should find out that x equals to 2 times square root of 10 minus 1 squared over 10 minus 1. 10 minus 1 is 9. So x equals to 2. We open the brackets of this expression. Square root of 1 minus square root of 10 minus 1 equals to the square root of 10 squared, that is 10, plus 1 squared, that is 1, plus 2 times square root of 10 minus 1. So x in total equals to 2. Inside the brackets we have 10 plus 1 is 11, plus 2 times square root of 10. So in total we should find out that x equals to 2 nines times 11 plus 2 times square root of 10. X is the radius of this small green circle. Our test is to find out the area of this green circle. The area of this green circle equals to pi x squared, because x is the radius. The area of the green circle equals to, actually the area of green circle equals to pi times the root of the circle squared. Therefore, the area of the green circle must equal to pi x squared because of the fact that the radius equals to x. So it is pi x squared. X is 2 nines times 11 minus 2 times square root of 10. So we substitute x by this expression. So this expression in total equals to pi, open the brackets. Here we have the squared, or this expression is squared. So it is 2 9 squared. 2 9 squared is 2 squared, that is 4, over 9 squared, that is 81. And we have to square also this expression. 11 minus 2 times root 11 minus 2 times root of 10 squared. So in total, if you want to know that the area of the rings 1 second equals to 4 pi over 81. Here we open the brackets of this expression. 11 minus 2 times root of 10 squared equals to 11 squared, that is 121, plus 2 times root of 10 squared, that is actually 2 squared, that is 4, times square root of 10 squared is 10, 4 times 10 is 40. So in total, this expression squared is 40. And we have minus 2 times 11, this is minus 22, minus 2, minus 22, minus 2 is minus 44, times root of 10. According to algebraic identities, it said that a minus b squared equals to a squared plus b squared minus 2 times a times b. So in total, we should find out that the area of the green circle equals to 4 pi over 81. So in the brackets we have 122 plus 40, this is 161, minus 2 times root of minus 44 times root of 10. So in total, we found out that the area of the green circle equals to this expression. Again, 121 plus 40 is 161, minus 44 times root of 10. Repeat again. The area of the green small circle equals to 4 pi over 81, and again 141 plus 20 is 161, plus 44 times root of 10. This expression in total equals to 274.7 square inches in size. So in total, we found out that the area that we are looking for this question, that is the area of this green small circle, equals to 274.7 square units in size. So we finished to repeat on the first question. The next step, I repeat on the solution of the second question on both methods. The second question, our test, is to find out the area of this quarter circle AOB. So in the drawing, we have quarter circle AOB. This is a right angle, this is also a right angle. We know that OQ equals to PQ, QB equals to 1. Again, our test is to find out the area of this quarter circle AOB. So we start with the first method. We define the radius of this quarter circle AOB as x. So AO equals to OB, the above the radius of the quarter circle, therefore each of them equals to x. OQ equals to OB minus QB. So OQ equals to OB, that is x, minus QB, that is 1. So in total, OQ equals to x minus 1. But because of the fact that PQ equals to OQ, and OQ equals to x minus 1, then PQ must also equal to x minus 1 units in itself. In the next step, we completed this quarter circle to a circle, and we extended the radius BO by a third line until it touches the circle. We define the touching point of the extended radius BO with this circle. This point is point N. ON is of course the radius of the circle, this is x. Because point O is the center of the circle. So ON equals to x. In the next step, we extended line segment PQ by a third line until it touches the circle. We define the touching point of the extended line segment PQ of this circle. This point is point M. Actually, QM is the mirror image of PQ. Again, QM is the mirror image of PQ. Why? Because if we divide the circle to two semicircles, we have the upper semicircle and the lower semicircle. And B is the axis of symmetry between those two semicircles. Again, and B is the axis of symmetry between those two semicircles. So if we fold this semicircle, if we flip the upper semicircle towards us, those two semicircles will merge with each other, and also point P will merge with point M. Point P will merge with point M. For that reason, again, Q1 is the mirror image of PQ. So if we flip the upper semicircle towards us, point P will merge with point M. That is to say, QM equals to PQ. But PQ equals to x minus 1, therefore QM must also equal to x minus 1 units instead. In the next step, implemented Rule 65 in our drawing. Please click on Rule 65. According to Rule 65, Rule 65 is true in any circle, so this circle could be any circle. In any circle, if chord AB intersects with chord CD at point O, then the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement Rule 65 in our drawing. Because in our drawing, we have chord NB. It intersects with chord NM at point Q. Again, chord NB intersects with chord PM at point Q. Chord NB intersects with chord PM at point Q. So all the requirements of Rule 65 are satisfied, and therefore we can implement here Rule 65. According to Rule 65, the following equation is to NQ times QB equals to PQ times QM. Again, NQ times QB equals to PQ times QM. NQ times QB equals to PQ times QM. This equation is the implementation of Rule 65 in our drawing. NQ equals to NO, that is x, plus OQ, that is x minus 1. So total NQ equals to x plus x, that is 2x minus 1. So NQ equals to x minus 1, QB equals to 1, PQ equals to x minus 1, is equals to PQ times QM. PQ is x minus 1, and QM is also x minus 1. So total, she found out that 2x minus 1 times 1 equals to x minus 1 times x minus 1. 2x minus 1 times 1 is 2x minus 1, is equals to x minus 1 squared. So 2x minus 1 equals to x minus 1 squared. We open the brackets here and found out actually that x minus 1 squared equals to x squared plus 1 squared plus 2 times x times 1, that is minus 2x. So total, we found out that 2x minus 1 equals to x squared plus 1 minus 2x. Here we subtract 2x from this equation, and we found out that here we left only with minus 1, and it equals to x plus 1 minus 2x is minus 4x. So in total, we found out that minus 1 equals to x squared plus 1 minus 4x. Here we added 1 to this equation, and we found out that here on this side of the equation we left with nothing, while on the other side of the equation we have x squared plus 1 is 2 minus 4x. So in total, we found out that x squared plus 4x plus 2 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is as follows. Ax squared plus bx plus c equals to 0. This is the general formula. A, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula. X equals to minus b plus minus 4 to b squared minus 4 times a times c over 2a. Now a specific quadratic equation, that is to say x squared minus 4x plus 2 equals to 0. The variable that we are looking for is x, and x is the radius of this quarter circle AOB. The coefficient a equals to 1, the coefficient b equals to minus 4, and the coefficient c equals to 2. So we have all the data that is needed in order to find out the value of x, that is the radius of the quarter circle AOB. Just have to put the data inside the general formula for x, and this way we find out the value of the values of x, because x might have two solutions. So we did it, and we found out that x equals to minus b. B is minus 4, so minus 4, minus b is minus 4, that is plus 4, plus minus quarter of b squared. B is minus 4, therefore b squared is minus 4 squared, that is 16, minus 4 times a times c. So it is minus 4 times a. A is 1, so minus 4 times 1 is minus 4 times c. Minus 4 times c is minus 4 times 2, that is minus 8. Divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, we found out that x equals to 4 plus minus 16 minus 8 is 8, so inside the root we left only with 8 over 2. X equals to 4 plus minus square root of 8 over 2. We substitute h by 2 times 4. And so now we found out that x equals to 4 plus minus square root of 4 times 2 over 2. We took 4 out of the root, the square root of 4 is 2, so inside the root we left only with 2. So in total we found out that x equals to 4 plus minus 2 times square root of 2 over 2. 4 over 2 is 2, and 2 times the square root of 2 over 2 is square root of 2. So in total we found out that x equals to 2 plus minus square root of 2. And again, so now we found out that x equals to 2 plus minus square root of 2. So here we have two solutions that are possible for x. The first solution for x is as follows. X equals to 2 minus square root of 2. 2 minus square root of 2 is 0.59. So according to the first solution for x, the radius of the quarter circle x equals to 0.59 units in its length. But we already found out that OQ, I said OQ equals to x minus 1 units in its length. OQ equals to x minus 1. OQ is a length, and as a length it must be a positive number. OQ equals to x minus 1, so x minus 1 must be a positive number. What is a positive number? Positive number is a number that is greater than 0. So x minus 1 must be greater than 0. Here we added 1 to this inequality, and we found out that x must be greater than 1. If x must be greater than 1, x can never be equal to 0.59, that is less than 1. So we cancel the first solution for x, and took into account only the second solution for x. And the second solution for x is as follows. X equals to 2 plus square root of 2. X equals to 2 plus square root of 2. Our test is to find out the area of this quarter circle AOB. The area of quarter circle AOB equals to pi x squared over 4. Because x is the radius. The area of the quarter circle AOB equals to pi x squared over 4 square units in size. So it is pi over 4 times x squared. X is 2 plus square root of 2. Therefore x squared is 2 plus square root of 2 squared. So in total the value of this expression is 9.155 square units in size. So we found out that the area of this quarter circle, that is the area that we're looking for, the area of quarter circle AOB equals to 9.155 square units in size. So we finish to repeat on the first method. In the next step, repeat on the solution of the second method. In the second method, we define the radius of this quarter circle AOB as x. So AO equals to OB equals to x, above the radius of the circle, on the quarter circle. OQ equals to OB minus QB. OQ equals to OB is x, minus QB is 1. So total OB equals to x minus 1 units in its length. But because of the fact that PQ equals to QO and QO equals to x minus 1, therefore PQ must also equal to x minus 1 units in its length. In the next step, we join points O and P together by side line. By joining points P and O, we can get the right hand triangle OPQ. First of all, point O is the center of the quarter circle, point P is the point on the quarter circle itself, therefore OP is the radius of the quarter circle, is equal to x according to our definition. So in the next step, we implemented Pythagoras theorem on this right hand triangle OPQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right hand triangle OPQ, OP squared is the square of the hypotenuse equals to PQ squared plus QO squared. Again, in the right hand triangle OPQ, according to the Pythagoras theorem, OP squared is the square of the hypotenuse equals to PQ squared plus OQ squared. OP is x, therefore OP squared is x squared, and it equals to PQ squared. PQ is x minus 1, therefore PQ squared is x minus 1 squared, plus OQ squared. OQ is also x minus 1, therefore OQ squared is x minus 1 squared. So in total, we found out that x squared equals to x minus 1 squared plus x minus 1 squared. That is to say, x squared equals to 2 times x minus 1 squared. So x squared equals to 2, we open the brackets of this expression, x minus 1 squared equals to x squared, plus 1 squared is 1, minus 2 times x times 1 is 1 to x. So x squared equals to, here we have 2, we open the bracket there, it is 2 times x squared, 2 times 1 is 2, and 2 times 1 is 2x is minus 4x. So in total, if you want to know that x squared equals to 2x squared plus 2 minus 4x. Here we subtract the x squared from this equation, and we found out that here we left with 0 after subtracting x, But on the other side of the equation, we have 2x squared minus x squared is x squared minus 4x plus 2. So total we found out that x squared minus 4x plus 2 equals to 0. This is exactly the same quadratic equation that we had in the first method. And we only found out that the solution of this quadratic equation is that x equals to 2 plus square root of 2. That is the only solution. Our task is to find out the area of this quadratic equation. Our task is to find out the area of this quarter circle AOB. The area of this quarter circle AOB equals 2 pi x squared over 4. Quarter circle AOB equals 2 pi x squared over 4. So it is pi over 4 times x squared. X is 2 plus square root of 2, therefore x squared is 2 plus square root of 2 squared. And the value of this expression in total is 9.155 square roots in size. So in both methods, we found out that the area of this quarter circle AOB, that is the area that we are looking for, is equal to 9.155 square roots in size. Okay, thank you very much.